Okay, Assalamu alaikum everybody. So last week we had started on our topic of isoparametric elements, and we had used the one-dimensional element example to understand what this concept is, and we saw how basically this involves using a universal parent element to map onto our physical domain. The main purpose that we had introduced these isoparametric elements, as we saw, was that when we use arbitrary shaped quadrilateral elements for meshing our physical domain, we end up getting elements which are not C naught continuous. That is, the essential fields or essential variable is not continuous over the element boundary if we directly use these arbitrary physical elements. And in order to overcome this problem, we had introduced our isoparametric concept, and we saw how for these arbitrary quadrilateral elements, we basically use our bi-unit square parent element, which looks like this. Now this element has universal dimensions with the psi coordinates right here going from -1 to +1, and the eta coordinate going from -1 to +1. So this is the universal element that we use to map on to any linear arbitrary quadrilateral element. So it could be, as we mentioned before, it could be something like this or any other shapes that we've discussed before. Right. Now, the reason why we refer to these as isoparametric, as we had discussed, is because we use isoparametric, that is, we use the same parameters. In this case, we use the same shape functions to perform this geometric mapping. That is, the mapping going from the physical coordinate x and y onto our universal parent coordinates psi and eta. So we use these shape functions right here. And we also use these same shape functions to perform the interpolation of our essential variable. So this expression right here. That is, each of our x, y, and temperature are being interpolated using our same shape functions N4Q defined over our universal element. Right. So this is how far we had got, and at the end of last week I'd left you an example to do. So essentially what this example involved was that we wanted to use our quadrilateral isoparametric mapping. That is, essentially we were going to use this 4-noded linear parent element to map onto our arbitrarily shaped linear quadrilateral element. And what we want to do is that we want to find the physical x and y coordinates of the point which corresponds to 0.5, 0.5 on our parent element. So a point that lies here. So we want to figure out what is the physical point that this point corresponds to, right? So in order to do that, we have already seen now that our mapping is done using our shape function. So x is basically given by the summation of, or you could write it in matrix form as well, that's also fine. N4Q evaluated at our given point multiplied by the nodal physical coordinates for each shape function or for each node, right? So this is how we find our physical coordinates. So clearly we need to find each of our shape functions at this given point. So that would probably be helpful, that we just directly find our N4Q matrix or row vector. So this of course contains N1, N2, N3, N4. So I'm just going to write out how long it is, and then let's find N1. So actually let's just write down that we're finding, at the coordinate 0.5, comma 0. This is, where is, how do I get? Yes. Okay, so that is, I'm finding n for q at 0.5 by 0.5. Please excuse these random lines popping up. I still have not figured out how to get rid of them. If you know what's happening with PowerPoint, please do let me know. Okay, so let's calculate this. So we're substituting in this coordinate right in here. So clearly for n1, I get 1 minus 0.5, 1 minus 0.5. So that turns into what? 1 by 4 multiplied by 1 by 4 multiplied by 1 minus half, which is a half, and then multiplied by 1 minus half again, which is also a half. So that gives me that n1 at this point is 1 by 16. So I can write that down in my N4Q matrix. Great. Similarly, if I find my N2, that would be 1 by 4 multiplied by 1.5 multiplied by 0.5. So that is 3 by 16. And N3 is 1 by 4 multiplied by 1.5 multiplied by 1.5. So 3 by 3, so that is 9 by 16. And then finally N4 would be the same as N2. So that gives me 3 by 16 for this case. Great. So now that I have my shape function matrix, then I can jump to finding my x physical coordinate. So that gives me this interpolation. So n1 multiplied by x1 clearly. So 1 by 16 multiplied by x1. So this one right here, x1. I need the coordinate 2. So multiplied by 2 plus n2, that is 3 by 16 multiplied by x2, so that is a 4. Please note node 2's x coordinate, so that gives me this. And then similarly n3 multiplied by x3, which in this case is 2, right here, you can see right here. And then finally n4 multiplied by x4, which is 1. So adding all of these up, I get that x is 35 by 16, which is, in other words, equals to a coordinate of 2.1875. Great. Now we could perform the exact same procedure, but this time for our y coordinate. And if we do that, instead of using our x nodal positions, we basically need our, so n4q multiplied by the respective y coordinates. And I won't go into it, please try it out. Basically what we get for our y physical coordinate is that y is 3.25. So what does that mean? Basically, that our point, this one, 0.5 by 0.5, is, as we've just found out, coinciding, or it corresponds to a physical coordinate of 2.1875, so somewhere here, 2.1875, and a y coordinate of 3.25, so somewhere here. So it corresponds to basically this physical point. So this thing is mapping onto here. That's what we know. So the usefulness of this isoparametric concept then is that we can use these arbitrary quadrilateral elements, but instead of using them directly, we use our isoparametric representation such that we will find our temperature interpolation, if we so wanted to, T, at this point in our natural coordinates, and then we can using our mapping, we can know where which point this corresponds to in the physical domain, so that if we know the temperature here in the natural coordinates, then that means that we know our temperature on this point in the physical domain, right? And using this approach, it turns out that our essential variable is continuous over these element boundaries. Great. Okay. So thus far we've just looked at our linear quadrilateral element, but actually we can even use higher order elements. Now by order, you may recall what we mean is that instead of our linear quadrilateral element, we can use either quadratic or even cubic and further on elements. Right, now the beauty of using these higher order quadrilateral elements is that they actually allow us to model curved edges. So this is best shown by looking at a higher order quadrilateral element. So let's consider our 9-noded parent quadrilateral element. So this is my the same bi-unit square, but this time around the shape functions are actually quadratic. That is, they are going up to powers of 2, right? So this is actually a, please note, I'm not talking about a quadrilateral, I'm talking about the power that the shape functions are going up till. So this 9-noded quadrilateral element is actually quadratic, okay? That is, the shape functions are not linear anymore, they are going up till powers of 2. They are quadratic in their order, right? So, our quadratic quadrilateral element consists of having 9 nodes. Now these essentially are the 4 nodes as before at the corners, but then 1 node placed at the midpoint of each of our edges and 1 node placed at the center of the element. Now this parent element or this universal element can map physical elements which are essentially having curved edges. So an element that could look something like this. Now this is extremely useful, as you can see, because this allows us to use fewer elements to model to get basically a better or a more convergent result, or to be able to better map curved boundaries, such as the previous example that we've seen of a circular hole. So previously we'd been using straight lines to model that hole, right? So we of course will need a large number of straight lines to be able to do that. Whereas now if we use these higher order isoparametric elements, then we can use fewer elements because they allow us to model the curved edges in the physical domain. Right, now how do we write down the notation for this? So basically, please note that because this has 9 nodes and it is a quadrilateral element, quadrilaterally shaped, so we tend to represent its shape functions using the superscript, that is n superscript 9q. So 9 for the number of nodes and q for the fact that it has a shape which is quadrilateral. Okay, so the 9 is basically telling us that it is a quadratic, that is powers going up till 2 for the shape functions, right? And as before, each of our geometric mapping, that is x and y, and our temperature or essential variable interpolation is performed using our same shape functions, right? So I'm only going to go over the concept of these higher order quadrilateral elements. I'm not going to actually discuss what these shape functions for this element look like. So we're not actually going to discuss what the expressions are for expressions within this N9Q, right? So same as how we've discussed isoparametric concept for quadrilateral elements, it can also be used for triangular elements. So even though we had, as we discussed, that this entire concept was initially introduced because of the issue with using arbitrary quadrilateral elements, we end up basically still implementing it even for triangular elements, even though it brings us no benefit. Okay, it's important to note that triangular elements are completely fine to use in the physical domain. They have no issue. They are C0 continuous. However, once commercial software were written out, they were just written out in sort of one format, so that you didn't really need to distinguish between what shape the element was. All different shapes of the elements all were written out using the isoparametric concept. Okay, so in this case, our the universal element essentially look like right angle triangles. So our three-noded right angle triangle, now three-noded universal triangular element, essentially, of course, this is our linear triangular element. And then we also have our six-noded parent element. Now this six-noded element is a quadratic one. Okay, so this has linear shape functions. This is a linear triangular element, as you can see from the expressions for the shape functions. And the one right here, this one is quadratic. So please look carefully at the shape functions for the six-noded triangular element. You can see that there are terms going up to powers of 2. Now we will carry on using our sign convention for our parent elements, which is that we tend to use a superscript to represent that these are actually our universal elements. So in this case, because we have a triangular shape, we use this T right here. And then the number before it, 3 right here, represents that it is 3-noded. So this is a N1 of the 3T element, that is the 3-noded triangular element, whereas right here we have N1 for 6T, that is the 6-noded triangular element, right? Okay, so in this case, for each of these, both for the 3-noded and the 6-noded triangular element, again we have used our psi and eta coordinates for 2D, but the psi basically goes from 0 to +1, and eta also similarly goes from 0 to +1. Now there's also another concept which does not use these psi and eta coordinates. Instead, something else is used which are referred to as the triangle's area coordinates. Now we will not be going into this concept right here, but I just want to mention that for you, that that's a special topic related to using isoparametric triangular elements, which you can look up in a textbook if you want. Sometimes it can be useful not to use this psi and eta. Anyway, we will not go into it right now. Okay, so now comes the tricky part, which is to look at the derivatives of these shape functions. Recall that often when we're Often in our weak form, we have the derivatives of our essential variable popping up. So for example, in our weak form for our heat conductance problem, we had del T arising, right? Now, if you're using our shape functions, that is to interpolate the temperature, then basically when we're finding del T, then we need to find the derivatives of our shape functions. Now this is exactly what our B matrix used to contain. So we were using our B matrix, this BE, capital BE, which contained within itself the derivatives of each of our shape functions with respect to the x and y coordinate. Now this is quite important, that our weak form exists in the physical domain. So when we're finding the derivatives, we actually need to still find our derivative with respect to x and with respect to y. So that's what we'll deal with in this part. So this is going to be a pretty intense slide, but just bear with me and go through it slowly, and hopefully things will be clear. Right. So as an example of finding the derivatives of our shape functions, I'm going to consider our four-noded quadrilateral element. That is, we're going to take this, our bi-unit four-noded quadrilateral element in the, of course, the psi and the eta domain. Why? Because now this is our reference parent element. This is the one that we use for finding our shape functions, right? So this is the element that we're going to use as an example, hence why I have my n's being represented with a superscript of 4q, right? Now, recall that we know what our shape functions are in terms of psi and eta. So let's say I'm talking about my n1 for this 4q. I already know what this expression is. You can see it in 2 slides before or 3 slides before. So it's very easy basically for me to find the derivative of this shape function with respect to either psi or with respect to eta. That is to find del n1 with respect to del psi. I can very easily calculate this, and I can very easily find my del n1 with respect to del eta. So how do I go from having these to finding del n1 with respect to x and del n1 with respect to y? That's what we're dealing with. So first of all, what we had already discussed in 1D is that what we do basically is that we use our chain rule. So recall that I can represent my derivative of n1 with respect to del psi using the chain rule in 2D by representing it as a derivative with respect to x, so del n1 by del x multiplied by del x by del psi, plus also any other variable that n1 may depend on, in this case which is y. So del n1 with respect to del y multiplied by del y with respect to del psi. Right. So basically we've got our expression for something that we already know, this one, in terms of the things that we want to get to. Right. And I'll remove the lines in just a second. Using the same concept of the chain rule, I can also write down my derivative of n1 with respect to eta. So del n1 with respect to eta is basically this expression right here, del n1 with respect to del x multiplied by del x by del eta. Similarly here, plus added on del n1 by del y multiplied by del y with respect to del eta. So this is the key part here. So we are using our chain rule to represent things that we know in terms of things that we want to find. Nice. Okay. So now let me write this down in terms in matrix form. Let me write that these two expressions down in matrix form to make our lives a little bit easier. So in matrix format, I'm just going to keep these on my left hand side, and then I can see that there is basically something popping up. So del x by del eta is popping up on my first term for my first equation and also on my first term for my second equation. So I'm just going to, sorry, del x by del eta pops, I apologize, del n1 with respect to del x appears in my first term for my first equation and for my first term for my second equation. So I'm basically going to take that out as a multiple and represent this essentially these two expressions in matrix format. So I get this expression right here. Please feel free to expand it out to see that I do get these two equations right here. Okay, so now what we want to do is recall that essentially it's these that we're trying to find, the derivatives with respect to x and y. So how I can do that is basically by inverting this expression. Inverting that expression to get this in terms of the derivatives with respect to psi and eta. Now, just to make my life a little bit easier, because inverting it and representing it is it's more useful to write it more compactly by representing this expression right here. So this matrix by this symbol J of that element E. Now the reason why this is called J is because this is actually a concept in coordinate transformations that exists anyway. This is basically referred to as the Jacobian of the mapping going from x to eta. Right? The Jacobian basically consists, this is a concept independent of the finite element method. This just is a concept in, let's say, even in image processing and other such things. Wherever you have coordinate transformations, the Jacobian arises. Now, wherever you have mappings, the Jacobian arises. The Jacobian basically just consists of the derivatives of our physical element with respect to our parent coordinates. So it contains del x, it just is this matrix right here. So representing this matrix by J, then I can represent the inverted expression much more easily, so that I find what my derivatives with respect to x and y are, just by noting that those are just then equal to the inverse of the Jacobian being multiplied by the derivatives with respect to psi and eta. This just follows from this expression right here. Right? Okay, now what is within the inverse of the Jacobian? Of course, for our particular case in 2D, it just consists of a 2 by 2 matrix. So it's straightforward for us to find the inverse. Of course, it is equal to 1 divided by the determinant of the Jacobian, multiplied by these two, in case somebody has forgotten what the inverse of a 2 by 2 matrix is, the diagonal terms swapped with each other and the off diagonal terms just having a minus added on to them or minus multiplied to them. Right? So this is the inverse of the Jacobian, and basically using this Jacobian we can find our derivatives in the x and y coordinate system. Now I just want to point out a few things. Maybe actually in just a second, let me see what's coming up. Yes, actually I'll just do it now. So note that I had been using just n1 as an example to show you how we can find the derivatives of n1 in the physical coordinates, given that we actually know n1 in the psi and eta coordinate. But remember, we need to do this for all of our shape functions. We need to do it for n2, n3 and n4 in order to find BE. Right? So very carefully take a look and have a think how we can write BE, all of it, given that we know that just this, the first column is given right here. So how can we expand it out? Let's have a think. So if I have that term in my first column, I'm going to use the part right here. So this is basically del by del x and del by del y columns of n1 term right here and I apologize, n1 term right here, then n2 term here, then n3 and n4. This is what we need, right? BE. So how do we find it? Using this expression that we just come up with. So clearly the first column is given right here. So that consists of the Jacobian inverse multiplied by del by del psi and del by del eta of what? Of n1 first of all, right? I'm just using this to represent the rows and n1 here to represent the column. Okay, you know that actually there is n1 here, n1 here too. Okay, so that's what I have for my first column on the left hand side. Now what I could do, actually I think maybe it's a bit more clear if I write this down right here. So n1. Now if I want to get to my second column, then all I need to do to represent my entire BE is basically to expand this right term with the respective del n2 with respect to del psi, del n2 with respect to del eta, and then for my third column, in order to find del n3 by del x. I hope you all understand that all of these are del x's. Yes, so to get my third column, all I need is to include my del n3 with respect to del psi and del n3 with respect to del eta, and finally also for del n4 with again respect to del eta and del n4 with respect to del psi. So this, the inverse of the Jacobian multiplied by this basically 2 by 4 matrix will give us our B matrix. That is, will give us our derivatives of the shape functions in the physical coordinate system, right? So that's just taking this expression right here and expanding that out for each of our shape functions. Right, now let's move on actually to looking at the Jacobian and how we can find the Jacobian. Now what's important is to note that let me put in, so many lines. Let me put in a little bit of separation right here, that I want to now look at finding just the Jacobian, this one. Now this Jacobian, as we've just discussed, contains the derivatives of the physical coordinate with respect to the parent coordinate, right? So it's JE is equals to this expression right here. Now also what I want you to do is recall that we actually already know what x and y are in terms of our, or what the mapping of x and y is in terms of our psi and eta. Remember that we were using our isoparametric shape functions where we were using these shape functions to perform the mapping, right? So x, this del x, this x in terms of the shape function is given by these expressions right here. So what I can do is actually to expand out the Jacobian even more. Of course I have to do that, I am trying to find the Jacobian. So if I don't know what x is this one. So how do I find this expression basically? What I need to do is basically then to substitute in this N4QXE in here. And similarly my y, which is N4QYE, right in there, and then solve for it. One easy way to do that would be to actually consider that we get this Jacobian, this one right here, by, what is that? It's actually the derivative del by del eta, del psi, and del by del n. So this is a what? A 2 by 1 multiplied by a 1 by 2, that is an x and y, right? So a 2 by 1 expression being multiplied by this 1 by 2 indeed gives me this 2 by 2 matrix that I have on my left hand side, right? So if I expand this out, multiply this, I get the Jacobian. Now I can also substitute in that I know my x is basically N4Q times xe and my y is N4Q times ye, right? So then that basically becomes this del by del e taken out and del by del psi right here. So they stay right here, but instead of the x and the y, I can write down N4Q, the n matrix, the n row vector basically. So this is again 2 by 1 and n is 1 by 4 multiplied by a let's say a matrix which contains xe and ye as each of its columns. That is, this has basically 1, 2, 3, 4, 1, 2, 3, 4. So multiplied by a 4 by 2 matrix. This is turning quite complicated. Let's take a look though. So 2 by 1 multiplied by 1 by 4 leads to a 2 by 4 matrix. 2 by 4 multiplied by 4 by 2 gives me a 2 by 2. So indeed I do get this back. Sorry. So now finally just look at this one, this expression on the right hand side, and I can expand that out basically to write down that the Jacobian is actually just equal to this expression right here. That is the derivatives of each of our shape functions with respect to psi and eta multiplied by the nodal positions, multiplied by the nodal coordinates. So that's how I can find this del x by del eta, del y by del eta, del x by del n, del y by del n, by using what I've got right here, this expression. Now again, I was trying to explain how we got to this matrix multiplication for the Jacobian. If you do not understand it, please go back, rewind it back, and just look at what I'd written out in the last in the last 5 minutes. Okay, I hope it'll be a bit more clear. If it isn't, we'll discuss it later on. Now, what ends up happening most of the time is that we are only provided this expression for the Jacobian. This is why I was trying to explain everything, because this is a standard function, as I've already mentioned to you, that the Jacobian exists in all sorts of different fields. And everybody, whenever you talk to someone and tell them that I'm looking at the Jacobian of this mapping, they know that you mean this term right here, right? But because we are using isoparametric finite element mapping, in this particular case, our Jacobian is then given by this expression on the right hand side. So it's important to understand how this is coming about. Right. Okay, so the easiest way to understand this then is to look at an example where I just want to, okay, so there is a little note. Although the shape functions do not depend on the element coordinates, yes, this is important. So note that we had been performing our isoparametric mapping so that we basically get these universal shape functions. That is, our N14Q or N4Q basically is fixed for all elements, it's unchanged. But as you can see right now, that for each particular element, when we are finding our, so N is fixed, the N matrix is fixed, but the B matrix, which is found using the Jacobian, is not fixed. That depends on which particular element we are mapping onto in the physical domain. Why? Because we can see in the Jacobian we have our element nodal positions. So we have x1, y1. So we basically, it depends where in the physical domain this element of ours is. So the Jacobian depends on the element, and hence the B matrix also depends on the element, and hence why we carry on using just the universal symbol for the N matrix, but B and J have the BE and the JE in their superscript because they are element dependent. They are not universal. Right, okay, so with that, let's look at an example. So what we're doing is that we have an arbitrary quadrilateral and we are using our isoparametric mapping to figure this out basically. So what we want to do is we want to find the Jacobian of this mapping. Now if you recall, for the Jacobian we actually first, this is our expression for the Jacobian, but when we expand this out, we see that we need our derivatives. Okay, I think I wanted to solve it, but I'm just going to go through it in the slides. We need to, when we expand this expression out, we got this expression to the right here, which contains within it the derivatives of each of our shape functions. So that means that we do need our shape functions, expressions, and we need to find basically the derivative of each of these with respect to psi and with respect to eta. So just expanding this out, clearly, okay, so what's the first term? Del n1 with respect to del psi. That is the derivative of this expression. N1 with respect to psi. So psi is, the coefficient of psi is just -1. So that just gives me what? -1 multiplied by 1 minus eta. -1 multiplied by 1 minus eta divided by 4. I've just taken the 1 by 4 out common. Similarly, I can find all of my other terms. Let's just look at another example. Let's look at del n4 with respect to del eta. So this one with respect to eta, this one. So the coefficient of eta is just +1. So what I get is just 1 minus eta divided by 1 minus psi, 1 minus psi divided by 4. And that's exactly what I have, 1 minus psi divided by 4. Great. So we can find these quite straightforwardly using our expressions, and then that is being multiplied by the nodal positions. Now node 1 is right here, it's 0, 0. Node 2 instead is what? 5, 0, so 5, 0. And then node 3 is at 3 by 3, so I have 3 by 3. And node 4 is finally at 0 by 5, so 0 by 5. Straightforward. Now multiplying these out, you have to be a little careful. It's a slightly involved matrix multiplication, but it's made easy by the fact that we've got some zeros in here. So please recall that this entire, for my first term right here, what gets multiplied? The entire first row gets multiplied by the first column to get this expression. Similarly, for this second one, I have my first row being multiplied by the second column, and so on. So be a bit careful about this. Now, so we've got our Jacobian. Now, why was I doing this entire exercise? Basically, if you recall from our last slide, if you recall right here that when we were finding our B matrix, and when we needed our derivatives with respect to the physical coordinates, this one, then that involved finding the inverse of the Jacobian. That is, to find the B matrix, I need to find the inverse of my Jacobian. Now this is exactly where this is exactly why we found this Jacobian, because what I want to see basically is, does the inverse of the Jacobian actually exist, so that can we actually find our B matrix or not. If the inverse of the Jacobian does not exist, then this element or whatever mapping that we're using cannot be used. That means that our mesh has an incorrect element within it. Okay, most of the time our finite element software have these sort of checks. We'll just discuss this in a second. Let's just first go back to looking at the inverse of the Jacobian. Now, in order for the Jacobian to be invertible, its determinant must be greater than equal to, it must be greater than 0. So it cannot be 0 or negative. So let's just find the determinant of the Jacobian to see what it comes out to be. So if I find the determinant of this expression right here, I basically get that the determinant is this value, this expression right here. Now please note that this determinant is not a constant. It depends on where we are. It depends on where we are in which point within the element we're looking at. That is, it depends on psi and eta. So if I look at this point somewhere here, that will have some value for the determinant. If I look at somewhere here, then it has some value. Now I just want to look at some of the extreme values. For example, when eta and psi and eta are both +1, so right here. So if psi and eta are both +1, then that basically means 3 minus 1 minus 1, which just leads to 1. So even then my determinant does exist and is greater than 0. So I can just perform this sort of a check that for our given values of psi and eta, the determinant is always greater than 0 over this entire element. So this mapping is okay, it's good. The B matrix will exist. So we're good to go basically. However, there are certain cases. So for example, if we had this mapping, right, what I've done is I've brought in my third node somewhere in here such that my angle, this corner angle, becomes greater than 180 degrees. Then if I find my Jacobian, I'm not going to do it right now, but then if I find my Jacobian, it turns out that the inverse of that Jacobian, or that is the determinant, becomes less than 0 at this corner, at these points right here, such that in this case the inverse of the Jacobian does not exist and we cannot find the BE matrix, which means that this mapping is no good. That is, this element or this particular physical element that we might have made is completely useless for us. So we cannot use such elements in our physical discretization which have corners which make an angle greater than 180 degrees, because these lead to a non-invertible Jacobian. And basically if you use these, you will get complete garbage in your finite element results. Okay, so most, as I'm just mentioning right here, that most modern finite element software do have some sort of a check that makes sure that these sort of elements do not exist in your mesh. However, it's good for you to know this piece of information just so that you can keep an eye out and make a check yourself as well manually. Right, now wherever you have a corner which has an angle greater than 180 degrees, basically what ends up happening is that this element is no longer convex. Okay, convex means that if you draw out a line through it, it would only cut it twice. Whereas look here, this is a non-convex element, or it is a concave element where you have the line cutting it 1, 2, 3, 4. It's cutting it more than 2 times. So non-convex elements are not allowed in finite element analysis. Great. Okay, so I have a few bits of, that's it for isoparametric mapping. I have a few questions for you to do as homework, which you have to submit on this Sunday, midnight, that's fine. So there are just 2 questions and they should not take more than an hour. So what I first want you to do is to actually show me that the Jacobian of this mapping is indeed non-invertible. Okay, please note that the third node is now at 1.5 comma 1.5. So find the Jacobian. And then the second question is looking at the 2D heat example that we'd already done. So this is the heat example that we are looking at, and we'd solved this problem entirely in the physical domain. But what I want you to do now is to actually look at one of its elements and use isoparametric mapping. Okay, isoparametric, now we're using linear triangular elements. So you use this parent linear, parent 3T element, and then find for me the Jacobian of this mapping, and also use the Jacobian to find the B matrix. Okay, so yes, these are due on 17th May. Finally, I just have a short discussion about assignment number 3. As I've already mentioned on the group that I am sending out individual feedback to every student, but it seems to me that a few of you have done a great job at finding an optimum solution, but some of you have actually not really performed an optimization at all. So I just want to give you another opportunity before I give you the final optimum solution. So I just want you to try it again. Please note that this is voluntary, it will not be graded, and all I want you to do is, instead of just carrying on increasing the size of the inspection chamber, to actually try to perform some sort of an optimization. And in order to help you out, I've outlined some methods that are useful for you to do. Number 1 is that because we're optimizing the strength to weight ratio, that is, we want the minimum possible weight of our bracket, you must actually consider the weight of your bracket and compare it for each of your iterative designs. How else are you going to show that your weight is, you've used the minimum possible weight in your final design? Next, please note that once you've got your analysis for a particular design, you can remove material wherever the stresses are very low within it. So for example, this is an example of a slightly optimized design. Even in this case, you can clearly see that there is almost this region of the design is unstressed. We don't need it, we could just remove it. Even this part can be completely removed. And that's exactly what this student has done. They've removed these bits and pieces wherever there were low stress regions in order to save material. And finally, just for your guidelines, you don't need to add in a very high factor of safety. So I'm going to leave this up to you. If you want to do it, please have a go again and send it to me. You don't need to send me a report, just send me your final design and considering your weight. So I'm just saying at most a 2-page submission. And then I'll share with you the most optimum solution that one of you has come up with or multiple students have come up with next week, inshallah. Okay, so that's it for today. Thank you very much. I'll see you on Thursday, inshallah. Take care.